want to just go through task 2 with you. It seems that some of you had a bit of trouble with it. So let me show you how to answer questions like this. So firstly, what I did was I gave you words, specifically I gave you words and I gave you compounds, well, the formula for some of them. So water, you needed to pull out like this. So the first thing you wanted to do was, is it a polar molecule, is it non-polar, or is it an atom? So water, we already know, is polar. So water is a polar molecule. How do you know this? Well, it's not symmetrical. It's symmetrical about that line, but not about that line. Okay, so that means that we do not have a symmetrical molecule. And you can also see that these are negative, what do you call them, lone pairs. So that means that side's negative. And remember, oxygen pulls the electrons towards it more strongly than the hydrogen. It's got a higher electronegativity. And so remember, hydrogen only has a proton left if it's one electron is going to the oxygen, which means that this side is slightly negative. So you can see that it is polar. Now, water is something very special because, yes, we could say dipole, because then you have to pick the intermolecular force. But it's not just a normal dipole. It is a very specific dipole, and that is the hydrogen bond forces. Remember, whenever oxygen is bonded to a hydrogen, or hydrogen to a nitrogen, or hydrogen to a, fluorine? Sorry, not nitrogen. Yes, nitrogen. Remember the NOF. Okay, nitrogen, oxygen, fluorine. Then we know that it's hydrogen bond forces. Okay, so what I wanted you to do was look at methane over here. Now, methane is a non-polar molecule. Okay, you can see it's clearly symmetrical, non-polar. And whenever you have non-polar, you're going to look at your rules and you will see that they are indeed London or London dispersion forces. You can say induced dipole. That also means the same thing. But London's just easier, London forces. So what happens here is what I want to just make sure you understand, that just because there's hydrogen here doesn't mean that there are hydrogen bonds. Okay, argon is just an atom. It's a noble gas. And so just an atom, a noble gas, is also London. Okay, fluorine, oh, you all fell into my trap, or some of you fell into my trap. Fluorine's a diatomic molecule. So it was actually a non-polar molecule. Okay, so not an atom, but it would have still had London forces between it. Okay. Then hydrogen sulfide. Now here's hydrogen sulfide. You can see it's polar. All right. It's very similar, in fact, to water, but because there isn't such a huge difference in the electronegativities like there is with the oxygen, we don't say hydrogen bond forces. We now say it is just dipole. Please remember that these are just forces between particles. So if I had another HH, so H2S, there would be a force of attraction between those two molecules, and between those two molecules would then be called dipole. Okay, it's not the bonds between the hydrogen and the sulfur. Okay, now this one I think tripped up a lot of you as well. This is hydrogen cyanide. Now you might say, oh, but there's hydrogen and nitrogen in here. It's not hydrogen bond forces because the nitrogen is actually bonded to the carbon and the hydrogen is bonded to the carbon. If the hydrogen was bonded to the nitrogen, that would be a different story. Okay, so, but this would then be non-polar and it would be a dipole between the molecules. So again, if you had another HCN, with this side being the negative side because of the lone pair, negative, the side positive, there would be an attraction between those two, and the force between those two molecules is called the dipole. Okay, I hope that helps. Please keep talking to me and let me know what's going on and what you're not understanding.